So, the data processing instruction, that is the first category of instructions that we have for ARM. So, it supports arithmetic large number of arithmetic operations like addition, subtraction and multiplication. So, one thing that you note here, that division is not supported. That may be taken as a disadvantage, but the problem is that supporting division. So, the division algorithm has to be implemented, and that way the architecture will become complex. So, if you really need division, then you can possibly do it using software, and many cases we may not need it. So, addition, subtraction and multiplication. So, these are the three instructions that are supported, and the multiplication has been made very powerful. So, that we will see that, and that takes care of this division operation to some extent. Then the bitwise logical operation. So, that is there. So, we can do logical operation. Then all operations, they take two 32-bit operands and return one 32-bit value. So, the internal, so it is 32-bit processor. So, all the operations are on 32-bit data. First operand and the result must be registered. So, this is the important thing, that the first operand that must be a register, and the result must also be a register. So, that is why it is a register type of architecture. Then the second operand, it can be a register or it can be an immediate value, and if the second operand is a register, it can be shifted or rotated before sending to the ALU. So, the first operand is a register and the second operand can be register or immediate. So, if it is a register, the value will be taken from the register directly. If it is an immediate operand, so that way the value will be available in the instruction in the instruction itself. So, the value will be taken from there, and if for registers, so you can do this shifting, rotating like that. So, that you remember that there is a barrel shifter and it is connected to the register file. So, from there it will be when it is coming, so it will be taking that register, the register value will come to that barrel shifter, and that barrel shifter will be shifting the value coming from the register. So, that way we can have this shift operation as a part of it. But if the second operand is an immediate operand, then the immediate operand must be 32-bit value. So, we must have a 32-bit value, and naturally we have a catch here, because the instruction itself is 32-bit, and then I am telling that the immediate operand should also be 32-bit. So, it is like this. Suppose I have got an add instruction. So, I say that add R1 comma say some 32-bit value, say 25 hex, and the result be stored in R2. So, meaning R2 will get R1 plus 25 hex. Now, you see that whole instruction is 32-bit, the coding of this whole instruction is 32-bit, and it says that this immediate operand, this 25 hex, so this should also be coded as a 32-bit number, and that is a problem. Okay. So, naturally you cannot represent all numbers in this 32-bit value, and what these ARM people have done. So, they have allowed only a category of 32-bit numbers that can be used as the second operand. How? Let us see. So, all 32-bit constants cannot be specified. So, the numbers which are allowed, then all binary ones must fall within a group of 8 adjacent bit positions and on a 2-bit boundary. So, what does it mean is like this. We have got this thing. Suppose this is the 32-bit number that I have got, and in that number, this is bit number 0, this is bit number 31. So, all these bits are say 0, in between you have got a block. Okay. So, if you mark the leftmost occurrence of 1 and the rightmost occurrence of 1, okay, in between the bits may be 0 or 1 whatever. So, this should be 8-bit, this should be 8-bit. So, the number the ones should be distributed in a block of 8 bits, and this block, it cannot start at arbitrary point. So, it has to be at 2-bit boundaries, like it can start at location 0, but it cannot start at location 1. So, it can start at location 2. So, like that it can go. So, this start point and end point, so they should be some multiple of 2. So, only those type of numbers, so will be able to represent. And how? how this can be done? So, if we just look back, it says that a valid immediate operand n. So, it is like this: I rotate right 2 into r, where I is a number between 0 and 255. So, it is an 8 bit number. So, this is between 0 and 255. Okay. This is between 0 and 255, and this r is between 0 and 15. So, if it is 0 and 15, so it is rotate right by up to, it can be 0 bit to 30 bit. So, after so many positions it can be shifted, but this r value, r can be equal to 0. So, in that case no rotation, r equal to 1. So, it is rotation by 2 bits, r equal to 2. So, rotation by 4 bits. So, you see that it is getting shifted by the even boundaries. So, you cannot have the number in odd boundaries. So, this, for example, the number 255. So, 255 you can represent in this format, because you can take I equal to 255 and r equal to 0, that is fine. Similarly, you can also represent 256, because I can take I equal to 1 and r equal to 12. So, if I take I equal to 1 and r equal to 12, then what will happen is that, so this I equal to 1. So, number is so if I take the number, so it is 0 0 0 0 0 0 0 0 0 0 0 0. So, this way ultimately 0 0 0 1, and I am rotating it right by 24 bits. So, it is 2 into r. So, 24 bits. So, I will be rotating it like this. So, if I rotate it, then this 1 will come to the position. So, where it is 1, then there will be 0 0 0 0 0 0 0 0. So, this is the number 256, and all these bits will be 0. So, you do the rotation and see that it will be a number like this. Okay. So, this will be this is the 32 bit number, and here this bit number 9 will be 1, and all other bits are 0. So, this way we can represent the number 256 in this particular format. Fine. So, all those numbers that can be fitted into this particular representation, so they will be allowed as immediate operand, others are not. Now, why is it useful? So, it is like this, that many times what happens is that for embedded application, so we have got this, say, the ARM processor, and we are getting some signal value from outside world, and this outside world value, so many of the cases they are only 8 bit values, though internally I am doing some 16 bit processing and 32 bit processing and all that. So, when we are taking values from the outside world in terms of, say, this ADC, analog to digital converters, or values of some digital switches and all that. So, if I are taking the value, so in many cases the values are only 8 bit wide. So, it is sufficient that I put, so in this 32 bit notation, these 8 bits will be located in a fixed position. Okay. So, these ones, the rest of the positions are not meaningful when I am getting this 8 bit data from the outside world. So, in many cases, so this is sufficient, this is good enough. Okay. So, we do not need to have 32 bit constants. Okay. And so, this is why it is done like this, that we have got this notation. And if you badly need more number of bits, like the numbers that are not fitted into this category, so for that purpose you have to somehow load that number into some register. You have to keep that constant in a memory location. From the memory location you have to load into a register, and after that you do the register operation as it is. So, there is no bar in that. So, you can always do that, but if you are willing to use as immediate operand, then we have to follow this convention. Okay. So, next we see that the modification, other things that we have, the modification of the condition flag by the arithmetic instructions, that is optional. Like the add instruction, we have got two variants, add and add-s. So, this add instruction, add R1, R2, R3. So, this will add R1 equal to R2 plus R3. So, R2 and R3 are added, and this is coming to R1. So, the operand format we have is, after the opcode we have got the destination, then the first operand, then the second operand. So, all instructions will follow this particular format. Then the next instruction, say add R1, R2, R3, LSL #2. So, this is basically the case where the second operand happens to be a register, and it is left shifted by 2 bits. Okay. So, this the overall execution is R1 equal to R2 plus R3 into 4. So, R3 will be left shifted by 2 bits. So, it will be multiplied by 4. So, R1 gets R2 plus R3 into 4. So, these two instructions, these two add instructions, they do not affect the status flags or the condition flags, whereas this addS instruction. So, this will affect the condition flags like addS R1, R2, R3, LSL has 2. So, this will be doing this same operation as R1 equal to R2 plus R3 into 4, but at the same time it will set the condition flags also. So, depending upon the result, if the result becomes 0, then the 0 flag is set. So, NZ, CV, so those flags were there. So, those flags will get affected. So, since this is setting is optional, so I have the flexibility, like if some instruction sets the flag, suppose this instruction sets the flag. So, I do not need to check the flag here. So, I can check this flag setting in some other instruction, provided the intermediate instructions they are all of this category, they are of the add type of instructions. So, they are not having this S in them, okay. They are not affecting the condition flag. So, these are the data processing instructions. Then we have got the data transfer instructions. So, the first category that we have is the data transfer instructions for transferring 1, 2 or 4 bytes of data between a register and a memory location. So, you can have 1 byte data transfer, 2 byte data transfer or 4 byte data transfer. So, total word size is 32 bit. So, you can have this 4 byte data transfer. So, base plus offset mode can also be used. So, you can specify a base and an offset, and then that way you can specify the address. Pre-indexed, post-indexed modes are also there. So, you can have this. We will take some example. Now, this offset can be 12 bit unsigned immediate value or a register shifted by another immediate value. I will take some examples. So, like this LDR, so LDR instruction is the load register, okay. The LDR stands for load register. Load register R0 within square bracket R8 means this register 0 will get the content from memory location R8, okay. Then we have got this is the indirect addressing. Then we can have this base plus offset type of addressing like LDR R0 R1 comma minus R2. So, R1 is the base address, R2 minus R2 is the offset. So, this offset is added, and then this is the content of that memory location will come to the register R0. Then we can have this offset as some immediate value also. So, R1 hash 4. So, R0 gets content of memory location R1 plus 4. Then we can have post increment. So, this exclamatory mark. So, this identifies it as post increment. So, R0 gets content of memory location R1 plus 4, and simultaneously R1 will be incremented by 4. So, this is the post increment mode, okay. So, it is base offset plus post increment. So, you can have something like this, that you can have this LDR R0 within bracket R1 comma hash 16. This is another way of writing this. So, here R0 gets content of memory location R1, after that R1 is incremented by 16. Okay. So, these are the different instruction formats that are available in ARM for the LDR instruction. Next, we will look into the other instruction like STR. So, these are the variants. So, LDR is for loading, and similarly STR is for storing. So, just the other way. So, you can say that STR some register to some memory location. So, content of that register will be stored in the memory location. Then the variants like LDR-H load half word, then STR-H store half word, then LDR-SH load signed half word, then store signed half word, LDR-B load byte, STR-B store byte. So, these are the various instructions that we have in load and store variants. So, this slide, so this will explain the difference between this big endian and little endian. Suppose we have got this register R0, it is a 32 bit register. Suppose its content is hexadecimal 10203040. So, they are distributed, the bytes are distributed like this. So, this 40 is in bits 0 to 7 and 10 is in bits 24 to 31. So, you have got this highest order byte in highest order portion of the register and the lowest order byte in the lowest order position of the register. Now, suppose we are executing this instruction STR store R0 comma within bracket R1, where R1 value is 0x200. So, in this 0x200 that location, so this is again a 32-bit location, then this if it is big endian format, then this higher order byte will come to the lowest address, then 20 goes to the next one. So, this is the first byte, so it goes to this location, 20 goes to the next location. So, you see ultimately this lowest order byte, so it has come to the highest order portion of the memory. So, if your memory is organized as 8-bit word, then this is the lowest address word and this is the highest address word. So, that way the lowest order byte has gone to the highest order memory location. So, this is the big endian format. On the other hand, if it is little endian format, then this lowest order byte will go to the lowest order address and this highest order byte will go to the highest order address. Like again the same thing, if it is byte organized memory, then this 40 will go to the lowest address, 30 to the next one, 20 to the next one and 10 to the highest address. So, that way it will go. So, as such there is no difference, like as long as you are reading and writing as words, 32-bit words. So, there is no difference between the two. But if you are doing a byte loading, like say this instruction LDRB load byte, then R2 register I will be loading the content of the memory location pointed to by R1. So, in this case R1 is pointing to the byte containing the value 10. So, 10 will be loaded, and in the little endian format. So, this R1 will be pointing, this location 200 will have the value 40. So, the 40 will be loaded into R2. The difference will come at this position. Otherwise, if you are reading writing word at word level, then there is no difference. Next, we look into this block data transfer type of instruction, and they are known as load store multiple instruction, LDM STM. So, this LDM STM instruction, so they are actually the variant of that moves instruction that we have in 8086 type of processor, as I was telling. So, you can transfer between 1 to 16 registers to or from memory. So, I will take an example, then I will come back to this. Okay. So, say this one, say suppose I want to transfer say for some data. So, this instruction, this LDM IA, so it will transfer 48 bytes of data, because R12 is pointing to the block where the source data starts. So, this they will be loaded into this R0 to R11 registers, total 48 bytes. Then this STM IA instruction, so it will be storing the values onto the location pointed to by R13. So, this way I can load store higher sized blocks onto this to transfer between CPU register and the memory blocks. So, this transfer registers, they are any subset of current bank of registers or any subset of user bank of registers in the privileged mode of operation. Can use base register, auto increment, auto decrement, etc. So, this is the thing, that is it can be utilized for implementing stack and moving large blocks of data around memory. So, in ARM processor we have I have told that the stack is not there by default. So, if you are willing to implement a stack, so you can use this load multiple and store multiple type of instruction for implementing a stack. So, we will see that. So, if you as far as the stacks are concerned, so there can be different variants of the stack, like say like this. So, if this is the memory onto which I am trying to implement a stack, so I can say, so if this is the lowest address, so this is the address say 0000 and the address increases in this direction, fine. And I have got this particular address from where the stack will start, and this address is say 1000, fine. Now, my stack maybe when I am doing a push operation, so it grows in this direction. So, stack pointer value after the first push, the stack pointer value becomes 999, then after the second push it becomes 998. So, it grows in this direction, fine. So, it grows towards the lower address. Okay. So, it grows towards the lower address. other possibility is that it grows towards the higher address. So, maybe after my stack grows in this direction. So, initially the stack pointer was 1000, after the first push the stack pointer will become 1001, after that the stack pointer will become 1000. So, it will grow in this direction. So, in this case I can say that it is a descending stack, this stack is a descending stack, because the stack pointer values are getting decremented. So, it was 1000 to 999 to 998 etcetera, and for the pop operation the stack pointer value will be incremented. So, this type of implementation is a descending stack implementation. On the other hand, here the stack pointer values are increasing. So, this will be called an ascending stack. So, the stack pointer values are incrementing with successive stack operation, successive push operation, and with the pop operation this stack pointer value will decrease. So, we have got descending stack, we have got ascending stack, both are correct. So, there is no doubt like which one is correct, which one is not. So, there is nothing like that. So, both are correct. So, any implementation can follow either of the conventions. Another convention that we can have is, say suppose I say that my stack starts at this point, okay. It is the location 1000, it is the location 1000. Now, at some point of time the stack has grown up to this much. So, it has gone to the location say 1020. Now, what does it mean? My stack pointer is here, my stack pointer is here. So, if the stack pointer is there, so there I can have two possibilities like, so it may have two meaning. One meaning is that the stack is actually full up to this point, up to this much it is full, and the next push operation will be filling up this location. So, this is one possible implementation. So, I can say that wherever the stack pointer points to is an empty location. So, that location is empty and the next push operation will put the data there. And other convention may be the stack pointer, instead of pointing to this location, it points to the previous location. So, in that case, for doing a push operation, I should first increment the stack pointer and then put the data onto the stack. So, this way I can have another classification. One is called full stack, and another is called, another version is called empty stack. So, they do not mean that the stack is full or stack is empty like that. So, full stack means that the stack pointer points up to points to the last field entry, in the stack, whereas this empty stack will mean that it is the stack pointer points to the next empty slot, it points to the next empty slot where the data can be put. Okay. So, overall, so I have got two more variants, one is full stack, another is empty stack. So, if I take these two and these two into consideration, so I can get 4 different types of stacks implemented: full descending stack, full ascending stack, empty descending stack and empty ascending stack. So, 4 variants can be there. So, ARM processor, they do not restrict you to have any of these variants. So, you can have all the 4 variants of stack, but you can you have to use your own instructions for doing it. So, you have to implement it separately. So, that is the only requirement, but this ARM processor will not stop you to that. On the other hand, if you remember 8085 or 8051, there is a specific saying like the stack pointer, it points to the empty port, the slot, and the push operation should first increment the stack pointer and then the value should be copied. That means, it is actually having some sort of a full stack implementation, and the stack pointer was always getting decremented. So, it is a full descending stack that we had there, but ARM processor will allow you to have any of the variants of the stack. So, coming back to our discussion, so we have got 4 different variants. So, descending or ascending and full, stack pointer points the last occupied address, or empty, stack pointer points to the next available address. So, we have got different variants of this instruction like store multiple full descending and LDMFD load multiple full descending. So, they are used for implementing a full descending stack. Similarly, STMFA and LDMFA full ascending stack implementation. So, store multiple full ascending, LDMFA load multiple full ascending. Then STMED and LDMED empty descending stack, okay, and this STMEA and LDMEA for empty ascending stack. So, we can have any variant. So, you should not mix up this instruction, like if you have used STMFD while for storing the values onto stack. So, while loading you should not use LDMFA, okay. So, then the values that you get will be corrupted, but otherwise there is no problem. So, if you are using the pair properly, then there is no problem. So, you will get getting the same values popped out from the stack.